Hello Chem 115 students. It's time to talk about units of concentration, some of which we have discussed in class, but I gather that more examples would always be helpful. When we talk about molarity, the point to remember is that it is another conversion factor. Molarity is represented by capital M, and we will use it as moles per liter when we're doing calculations to allow us to cancel out units and come up with something that's desired. When you're calculating molarity, you will simply divide moles by liters, but in other applications, it's a conversion factor. Be very careful how you write these things because capital M is not the same thing as MOL, small m. Aren't used the same way. What we can do, though, in understanding these kinds of calculations is realize that if you take moles of solute times, if you take the molarity times the volume, namely the liters down here in the denominator of this expression, that ends up with a way to calculate a moles of solute. In other words, moles per liter times liters gives you moles. And we use that often in doing some calculations. Now, the other thing that will surprise you, or if you weren't expecting it, haven't seen one for a while lately, is once in a while we're talking about small concentrations, and so you'll see a small m in front of the capital M, which represents millimolar. It's the same idea as milligrams, milliliters, milliseconds, what am I forgetting? Anyway, milli units are always 10 to the minus 3 times something. So it's 10 to the minus 3 moles per liter when you see millimolar. All right, some examples to try to make sure that's not too tricky. Let's see, if we're going to figure out the molarity of a solution, it says 0.4 moles of sodium chloride is dissolved in 100 milliliters of water. What is the molarity? So we need it to end up as moles per liter. And in order to do that, it's okay if you just start with what you've been given and then convert to get to the units that you need. So put in 0.4 moles and divide it by the volume. And it's always concentration is an amount of solute per volume. And 100 milliliters goes then on the bottom, but we don't have liters yet, so let's make a conversion step. And if you work problems in this chapter, you will get very comfortable, I hope, with this conversion between milliliters and liters, which hasn't been used for a little while, but comes up often now. And that will show you how milliliters should cancel. Take out a couple of zeros, make your life easier. And so 0.4 times 10 is all you have on top, and so the answer is 4.0, if you will. We don't need that many digits, actually. Okay, skip that. There's not that many sig figs. M is your answer, molarity, 4.4 moles per liter. The second example is very similar to one in the Pogel book. If you have 42 grams of sodium hydrogen carbonate dissolved in a given volume, 250 milliliters, and then we have to come up with molarity. Again, this is a series of conversion steps if you do it in a simple fashion. So let's follow through to realize that you're going to have solute on the top and solution on the bottom, and you'll do some conversions until you end up with moles per liter. So set it up that way and try not to round off any numbers before you get to the end to avoid making errors with significant digits. So the amount of solute in this question is 42 grams divided by the 250 milliliters. What we're aiming for is moles per liter, so we'll have to convert both the top and the bottom values to come up with moles and liters. Well, obviously we got milliliters. We know how to get rid of those. And so put in your 1,000 milliliters per liter, same as we used in the previous example. And that'll allow the milliliters to cancel. And then we have to figure out how to get rid of grams. Well, there is another conversion factor that will come up often in these calculations, and that would be molar mass. And the molar mass is given here, so you don't have to think it out. But it's also the same one we used in class and in the Pogel book examples. And so in order to make grams cancel, let's put the grams on the bottom from the molar mass provided for sodium hydrogen carbonates. So it's 84 grams per mole. And then what's next? Well, let's check out our units and make sure what's canceled and see if we're getting close to what we need. Having done this, the grams will now be canceled out, and what's left is moles on the top and liters on the bottom. Ta-da! That's exactly what we want. And I would do one further step to save my calculator error options and get rid of a 0 from the top and the bottom. And if you know what 100 divided by 25 is, and I do, I think it's like 25 cents in how many times in a dollar? It'd be 4. So I'm going to put the 4 up here. And guess what? This one is even simpler than that because I've set up some numbers for convenience. And so simplifying here, 42 goes into 84 an even number of times, namely twice. And so 4 divided by 2 is all we have in this calculation. And the answer would be 2. Let's see, sig figs, how about 2.0? Because we have 2 digits to begin with on our given quantities, the 42 and 250. And so 2.0 molarity, molar is another way of saying it, is our answer for this particular question. Let's try another one now, talking about dilutions. Dilutions are not difficult if we keep track of the idea that the molarity times the volume gives us a number of moles, but the number of moles you begin with is the same as the number of moles you end up with. And so we use M1 V1 equals M2 V2. If you carefully set up the calculation to figure out what's known and what's not, then you'll be able to use that relationship. A little bit of rearranging. It will be provided on a test, so you don't have to remember it or be worried about getting it correct. So 60 milliliters, well, that must be a volume. So let's write that up here. And always write these things down, otherwise you're likely to make errors. It is of the first amount, or the concentrated sulfuric acid. So it's molarity number 1. It's diluted to a new volume, so that would be volume 2. And so let's make it careful. Apparently what we're looking for is a new concentration. That would be M2. And so that we will find in this relationship. Let's start by rearranging the equation, but not the numbers. So M2 is going to be M1 times V1 divided by V2. And don't worry about being able to do the algebra. Look it up on the list of equations available for this next exam, and you'll realize that you don't have to remember it. Take my word for it now. And put the numbers in. So 18 molar is the first molarity, times the volume of 60 milliliters. Uh-oh, what do we do about the volumes here? Do we need to go to liters? Well, let's check it out and we'll deduce as we go. The bottom volume, the second one on the bottom, is 1 liter. Uh-oh, well, if we have milliliters and liters, we can't do them, it won't cancel out. So if you remember that there's 1,000 milliliters in a liter, then we won't need to take a separate conversion step here. Just write 1,000 milliliters instead of writing a liter. That allows us to cancel out the volume units, which we didn't need, and then you're going to have another 0 to get rid of. And this becomes a calculator exercise because I'm pretty sure you won't want to do it in your head. So pull out your calculator and do it with me. The number I arrive at in my calculator without any extra confusion, hopefully, is 1.08 with a lot of zeros after it. Now we should recognize that the unit on the answer should be M, molarity. That's the new concentration of this diluted solution. And for the number of digits in this question, it could be a 1 sig fig answer. Unfortunately, this first value didn't have a decimal on it. Well, if it did, which would have been more appropriate, then we would use a 2 sig fig answer. And so 2 sig figs, we have to keep remembering how to do our sig figs because they get out of practice once in a while. And that would be 1.1 molar. All right, fair enough. Let's see what else. Let's try another question that has you calculate a concentration. So iodine is a solid that dissolves in organic solvents because it's very much nonpolar. If you remember the experiment in the lab about solubility in solution, that's one that was tested. It will dissolve in this thing called dichloromethane, which gives a very pretty orange solution. What would be the molarity? If you take iodine And 5 grams dissolve in enough of this dichloromethane, you don't have to know anything more, to make 50 milliliters of solution. Again, this is solute divided by solution. So let's take 5 grams of iodine and start doing some conversion factors. Whoops, but let's divide it by the amount of solution, then start doing our conversion factors. So 50 milliliters, and 5 and 50 is going to make for some convenient calculations as we go. But we want to get grams to turn into, oh yeah, moles. So how do we get how many grams of iodine per mole? Well, get out your trusty periodic table and look it up. And remember that this is iodine I2, otherwise you'll get the number wrong. And 1 iodine has a molar mass of 127, so 2 iodine, I2 in other words, is 254 grams per mole. And then we would be able to cancel out grams. That's always advantageous, reassuring to validate that the units are coming out correctly, so be very cautious to write them out whenever possible. Now we need to have molarity in liters. So let's convert milliliters to liters. It's the same conversion that keeps popping up in these examples. 1,000 milliliters is going to be 1 liter. That will give us liters on the bottom, which is what we need to get molarity. And so let's see, what can we do next? Let's take out a 0, and we'll take 5 divided by 5. That might be 1. So on the top, all that's left is 100, and the bottom is 254, but that would be a calculator question, so go to your calculator. Always be sure you can do these on your own calculator, because that's where it's going to be when it comes to an exam. The answer that my calculator displays is 0.3 9, whoops, where's the number? 937. Oh, that's too many digits. You know you don't want that many. So look back at this question and recognize that the iodine was given as 5.0 grams, so that limits us because that's fewer digits than the 50 milliliters. So rounding this to 2 sig figs would be an answer of, think about it, you got it? It's going to be 0.39. And the unit is going to be moles per liter, so we write that as M, capital M. Not a hard problem to do, but make sure you recognize that all of these problems require conversion steps, and make sure you follow through to use things like liters to milliliters and molar masses as needed. Always this solute divided by solution gives you a concentration. Okay. Concentration units in weight percent are not too bad. We saw some conversion factors for things like this in the POGIL activity, but let's make sure we can think this one through carefully. So if you see this question, how many grams of potassium bromide are needed to make 20% solution and 200 milliliters? Well, then what do you need? Well, first of all, you have to recognize that the 20% means 20 grams per 100. That's what percent means. 100 what? Milliliters. Okay. So again, it's a conversion problem. Let's set it up and figure out where we're going. Oh, well, let's see. We start with a value that's not a conversion factor, namely the volume. And the 200 milliliters times something that gets rid of milliliters and ends up with grams. Well, there you go. Use that percent weight per volume restated as 20 grams per 100 milliliters. Well, guess what? This one's not too bad. You might have been able to do this without setting it up in a systematic way, but it's a good practice to make sure you see how it's done for other examples that are less obvious. All right, so milliliters cancels, the zeros cancel. 2 times 20 is 40 grams. In other words, if it takes 20 grams for 100 milliliters, it better take 40 grams for potassium bromide for 200 milliliters. Not bad. Now, how about another one? Would this calculation come out different if you wanted 20% weight per volume for sodium chloride? And the answer is, it is exactly the same. Oops, I'm sorry. Comes out exactly the same because there's nothing about the molar mass or anything, the particular elements in that calculation. So you can get 20, to get 20% sodium chloride in 200 milliliters, it's again 40 grams in 200 milliliters. Nothing about molar mass. Sometimes that's actually simpler. So don't argue when it is. Okay, let's find another one. If you want to figure out how many grams of sodium chloride are present in 150 milliliters of 20% weight per volume sodium chloride, set it up as a conversion problem again. Use a value that's not a conversion factor for your starting point. So take the 150 milliliters that we're going to put this solution in, make of this solution. Then recognize what the conversion factor has to be with the 20%. It's, in other words, grams of solute per 100 milliliters of solution. And so we'll put the 20 grams on top, 100 milliliters on the bottom, and then we'll figure out that the milliliters cancel, and you get grams. Cancel out some zeros, do yourself a favor. And so 2 times 100, take out another 0. 2 times 15, I bet some of you could do that. It, without a calculator, should be 30 grams. Fair enough. All right, what volume of 20% weight per volume sodium chloride contains a certain amount, namely 75 grams? Again, a conversion factor. So let's set it up, conversion problem. Start with a known value that is not a conversion factor, in this case grams, and then use the 20% weight per volume as the conversion factor. But this time, the 20 grams needs to go on the bottom because the grams will have to cancel. And then we're putting our 100 milliliters on top, and we're going to get a milliliter answer. And let's see, what can cancel out? Simplify these things before you hit your calculator. You save yourself a little bit of trouble. And let's see, 10 divided by 2, we might know that that would be 5. So 75 times 5, okay, maybe you don't know that one in your calculator. Otherwise, it would be 750, 75 times 10, divided by 2. And I bet some of you could get that one. Looks like 375. 375, what's the units then? Gram. Nope, it's not milliliters. I canceled out the grams. There we go. Milliliters. Remember that's, I forgot to mark out the grams as I was doing other simplifying. All right, there you go. Is that a 2 sig fig answer? Nope. So to 2 sig figs, that would actually be 380. But it depends on how much precision you want in these reported values. All right, trying to write my units here slowly. The toy doesn't work well. Now, the other units are percent volume per volume, which is exactly the same idea in the sense that you have milliliters per 100 milliliters. That's used for liquid solutions, not a big deal. And the other ones were parts per million, which were mentioned in the POGIL activity, which is a cousin to parts per billion. It's how many grams per a million when it's parts per million. And we remember that grams and milliliters are essentially the same because of the density of water. So as long as we're talking about water solutions, we can talk about a million grams is a million milliliters. Or parts per billion is how many milliliters out of 10 to the 9th milliliters, or grams, either one. Depends on how these things are stated. Let's try an example. Let's say if the safe limit for lead in a waterway is 2 milligrams per 1 kilogram, what is this if we calculate this to be parts per million or parts per billion? First thing to do is determine the number of grams of solute, which is what we need to know here, per grams of solution, and then to get a per million answer, this is like percent, you have to multiply by a million. So grams of solute, let's see, 2. Well, that's milligrams, but we'll have to get it to grams. We can do that with a conversion step. All of these things feel like conversion problems. And divided by the grams of solution. Well, we have a kilogram. So let's work each of these towards their respective states of being expressed as grams. So 2 milligrams of lead. Let's suppose we get rid of the milligrams first. So how many milligrams are in 1 gram? We want the milligrams on the bottom. It's like milliliters and liters. So there's 1,000. And so put that on the bottom. Allow the milligrams to cancel. And do the next step. So this is that would be for the lead. So we can leave that one labeled the same. It's going to feel funny because you're going to have grams in 2 places, but you usually do. These come out to be ratios of grams. And so when you're done, there isn't a gram in the answer. It's just a parts per million sort of thing. Now, to get kilograms converted to grams, let's see, kilogram has to go on top. And a kilogram is, if you can think back to chapter 2 or chapter 1, a long time ago, it's 1,000 grams. And then we can cancel out kilograms. Good, don't want that anymore. And now we have a math problem. We have, whoops, one more step. I forgot about making this one. Times 10 to the 6th, because we're multiplying by a million. Now we do the math. Okay, but this is where math in exponents can come to your aid, because 1,000 is 10 to the 3rd, and the denominator of this question has only got 1,000 times 1,000, which is 10 to the 3rd times 10 to the 3rd. And you know what? 10 to the 3rd times 10 to the 3rd is 10 to the 6th. So that actually all cancels out. And all that you're left with is the numerator of 2. So 2 parts per million, and that would give you a very quick calculation. So whenever you have milligrams per kilogram, that's exactly the same thing as the unit that you get for parts per million. If you wanted to do parts per billion, then you would have to do one step slightly different at the end. What do? Parts per billion, instead of having times 10 to the 6th at the end, it's all the same values, times 10 to the 9th. So apparently that's 10 to the 3, as in 1,000 times as much. And so the answer here becomes 2 parts per billion. Not too much to calculate there with a calculator. Sometimes you get lucky. All right, another example with parts per million, parts per billion, just to see if we can do these things correctly. It says dioxin is considered poisonous at levels above 2 parts per billion, and we want to find out if a lake is safe for fish if it contains 0.1 grams per 10 to the 7th liters. So again, you figure out how many grams of the substance and how many grams of the water, then you multiply by 10 to the 9th, remembering that water has a density of 1 gram per milliliter, gets you by when we're looking at liters up here. Okay, so 0.1 grams of toxin, don't have to write it in, and 10 to the 7th liters. Oh boy, we have to get from liters to grams of water. Oh boy. Well, let's do it. Liters, 1 liter is 1,000 milliliters. Yes, it is. So we can say 1,000 grams. It's the same thing. And so that simplifies that part a little bit. We didn't want grams anyway. Or we didn't want liters, sorry. And now we can get rid of the grams on this would be the solution, sorry, or the water. And then we have to just convert the top one also to do anything. No, we don't. We have grams already. So let's just take and multiply it times 10 to the 9th. And 10 to the 9th gives us a and time to do a multiplication step here, or some calculations. Now, 10 to the 7th on the bottom times 1,000, that's 10 to the 9th. Okay, no it's not. 10 to the 10th, add your exponents. 10 to the 3rd times 10 to the 7th is 10 to the 10th. And the numerator is 1/10 of 10 to the 9th, so we have 10 to the 8th. And on the bottom we have 10 to the 10th. And so that is subtracting the exponents, the top from the bottom, we get 10 to the minus 2, and the answer is in parts per billion because we multiplied times 10 to the 9th. And is it safe for the fish? Oh, it's way safer. It's not even 2 parts per billion. Oh, wait a minute, that was our unit that we were aiming for. Well, let's go backwards. That needs to be how the level for it to be safe. It has to be 1/100th parts per billion. And so let's make sure we've said this correctly. So if it's above 2 parts per billion, then it would be unsafe. So it's much less than that. It is going to be safe. Make sure I read the question correctly. Sorry about that, folks. All right, we're too busy looking at calculations sometimes. To help you out with molarity calculations, let's do a little bit more practice. How much potassium bromide is needed if you're going to make 1 liter solution 2 molar KBr? Well, how much? How much? Back up. Let's figure out what units we're looking for. Let's suppose that might be grams, because you have a volume here that you're making and you know the concentration. So how do you get to that? Well, remember, all of these things are like conversion problems. And so let's say we have 2 different things to look at here. 1 liter is not a conversion factor. 2 molar is, because it's moles per liter. Start with the 1 that is not a conversion factor. 2 moles per liter, put that in. Well, then the 2 moles goes on the top. 2 molarity, 2 molar. And the liters cancel, but we need to come up with grams yet, so that's where molar mass comes in. Put in your 119 grams per mole, and the moles cancel, and now we have a math problem. 2 times 119 looks like to me, and that would be 238 grams of potassium bromide. And is this the correct number of sig figs? Oh, probably we only need 2 here. So 2 sig figs, this should be 240 grams. Close enough for this calculation, in other words. All right, now let's do another one. And this one we have the question stated, how much potassium bromide, in other words, that's going to be grams again, is needed if you're going to make a liter solution and 0.3 moles per liter. So if we need to get grams, we'll start with the value that's not a conversion factor, 1 liter, and then put in the moles per liter over here. So 0.3 moles. If you put that on the top, the liter goes on the bottom, and it cancels out. That's advantageous. And then we need to get rid of moles because we can't measure moles directly. So we'll use molar mass, same as the previous example. And that's 119. Thank you for calculating ahead of time. Haha. And then 119 grams per mole. It allows the moles to cancel. And from there, we do a math question, right? Let's see. 0.3 times 119. Let's put in the calculator on this one. I don't think you're going to do that in your head. The answer I see on my display is 35.7. And what are the units now? Must be grams. But how many significant digits belong in this question? I bet this should be another 2 sig fig answer. So let's change that. Call it 36 grams to 2 sig figs again. So 36 grams is close enough. All right, I hope these examples have helped you to understand how to work some of these problems. Good luck with doing these various examples so that you'll be comfortable with them when it comes time for an exam.